Welcome back to AI Paper Slop. If you're fine-tuning models right now, you already know the massive headache of GRPO. Your model either stubbornly locks onto one single reasoning path way too early in training, or, if you try to force it to be creative, it just hallucinates into total instability.
Yeah, it completely falls apart.
Right. Well, today, we're looking at a paper that claims to have completely solved this. It's called Long Live the Balance, Information Bottleneck-Driven Tree-Based Policy Optimization by Hao Jiang and a team of researchers at Alibaba Cloud Computing.
It's a really impressive piece of work.
It really is. And for everyone building in this space, here's the core insight right up front. This paper introduces a metric called the IB score, which is grounded in information bottleneck theory to measure the exact mathematical trade-off between reasoning diversity and finding the correct answer.
Exactly. It quantifies it.
Right. And by using this score to guide a tree-based search, which they call IB tree, they're generating 50% more trajectories under the exact same token budget as standard GRPO.
Which is just crazy efficiency.
It is. And the results are massive. On Qwen3 models, it boosts accuracy by 2.9% to 3.6% across some of the most brutal math and coding benchmarks we have.
I mean, it's a fundamental shift in how we handle reinforcement learning for large language models. This isn't just like a theoretical math exercise. It solves the real-world pain of sparse reward signals in post-training.
Yeah, the sparse reward problem is so frustrating for engineers right now.
Oh, absolutely. Because when you're using outcome-based verifiers, you only get a signal, a 1 or a 0 at the very end of this massive chain of thought.
Just a pass or fail after pages of text.
Right. But by integrating this IB score, the framework forces the model to explore intelligently at the actual critical logical junctures of a problem, rather than just branching randomly and basically praying for a positive reward at the end.
Which is what we've been doing.
Yeah.
So to really grasp why this IB-TPO method is such a breakthrough, we need to look at the baseline. Like, we have to unpack what is actually breaking inside standard GRPO or group relative policy optimization during a normal training run.
Yeah, it's important to understand the failure mode first.
Right. So the paper maps out the training dynamics they observed in the Qwen3-8B base model. What is the physical reality of the model's behavior early in that training process? Like, what's happening under the hood?
Well, if you look at the training logs, what you see is this rapid, incredibly steep drop in policy entropy.
Like, it just plummets.
Yeah, exactly. The model essentially stumbles onto one single path that yields a positive reward, and it aggressively collapses its entire probability distribution around that one path.
Wow. Okay.
We refer to this as overexploitation. The model becomes overly deterministic far too quickly. It finds a trick that works once, and it just refuses to try anything else.
It gets lazy.
Essentially, yeah. And this leads directly to the collapse of a critical metric that the paper tracks, which they call the F rate.
Okay, let's define the F rate for the audience really quick.
Yeah.
It stands for the effective rate, right? Which is the proportion of sampled groups that actually have non-zero reward variance. Because if you think about how standard GRPO operates, this variance issue becomes the entire bottleneck of the training process. I mean, GRPO samples a group of trajectories, say, 8 different attempts at solving a complex Python problem. And it updates the model based on how each attempt performed relative to the average of that group.
But if the model has already collapsed its entropy, if it's just outputting the exact same sequence of tokens 8 times in a row, every single trajectory gets the exact same reward from the verifier.
Because they're all identical, which means the variance across that group is 0.
Exactly.
And the relative advantage for every single trajectory is just 0.
And the downstream effect of that is just catastrophic for learning. The learning signal completely disappears, your gradients vanish, and the model's performance just violently stagnates.
It just hits a wall.
It completely hits a wall. Now, if you look at standard ML engineering practices, the typical fixes for this are things like asymmetric clipping thresholds, which people often call clip higher, or injecting entropy regularization directly into the loss function.
Right, I've seen that a lot.
Yeah, the idea is to artificially penalize the model for being too certain, forcing it to keep guessing.
But I'm looking at the ablation studies in the paper, and those standard fixes basically fail.
Yeah.
I mean, they might artificially increase the overall statistical entropy of the model, but that crucial F rate still drops to 0.
They fail because naively pushing entropy regularization too high triggers what we call an entropy explosion.
An entropy explosion.
Yeah. The model doesn't start exploring better logical pathways. It just exhibits massive uncertainty across every single token. It completely destroys the stability of the training run and heavily degrades the model's performance.
It's like a student who memorizes exactly one highly specific, rigid way to solve a calculus problem. That's your overexploitation.
Oh, that's a great way to put it.
Yeah, they get it right once, and they refuse to try any other method because they know this one gets them the grade.
Yeah.
But if a teacher just yells at them to, like, be more creative, which is basically what entropy regularization does, the student doesn't suddenly start exploring brilliant new logical shortcuts.
No, they don't.
They just start blurting out numbers randomly. That's your entropy explosion. They aren't exploring the problem space. They're just injecting noise into the classroom.
That analogy hits the absolute core of the problem. Just injecting overall token-level uncertainty doesn't lead to effective exploration. You need the model to explore meaningful semantic branches.
Right.
You don't want it to just randomly swap out vocabulary words while maintaining the exact same flawed underlying logic.
So since blindly injecting entropy is a dead end, how do we actually measure and encourage effective exploration? I mean, this is where the authors bring in the heavy machinery, right? Information bottleneck, or IB theory.
Yes, exactly. So traditional information bottleneck theory is usually applied in deep learning, specifically to representation learning. The core idea is compression. You want to compress an input, basically discarding all the task-irrelevant information, all of the noise, while maximizing the mutual information with your target output.
So keeping only what matters.
Right. You are forcing the network to isolate only the features that actually matter for predicting the correct answer. But here, the Alibaba team does something highly novel.
What do?
They completely reformulate IB theory into a stepwise metric for LLM reasoning. They call it the IB score.
Okay, before we get into the heavy math, let's try to translate that traditional IB concept into plain English for language models. It's essentially about forcing the model to ignore the useless fluff in a prompt or a reasoning chain, right?
Basically, yeah.
And to only pay attention to the data that actually changes the final answer. But applying that to a step-by-step chain of thought requires breaking it down. What are the actual components of this stepwise IB score?
The stepwise IB score boils down to two main mathematical components, which the paper labels as eta 1 and eta 2.
Eta 1 and eta 2.
Okay. Eta 1 represents the information gained from the environmental feedback. You can kind of visualize it as the historical success rate of the subtree branching from that specific reasoning step.
Oh, interesting.
It essentially asks the environment, like, if I take this specific path based on my previous rollouts, how likely am I to eventually hit the correct answer?
So eta 1 is the objective environmental signal. It's the reality check. So what is eta 2?
Eta 2 is the policy model's internal confidence in that specific branch. It's the probability the model naturally assigns to taking that step based purely on its current weights.
Okay, makes sense.
Now, here is the absolute crux of the paper's theoretical contribution. The effectiveness of the IB score doesn't just come from pushing both of these numbers as high as possible.
Right.
It comes entirely from maximizing the covariance between eta 1 and eta 2.
Okay, wait, let's really explain covariance here because I feel like it's the secret sauce of this whole paper. Covariance isn't just about two numbers being high. It's about how they move together.
Right.
We want the model's confidence to scale proportionally with the actual usefulness of the path.
Yes. Balancing exploration and exploitation isn't about having high overall uncertainty. A positive covariance means the model is learning to strategically allocate its confidence, its eta 2, specifically to the branches where the environmental feedback, the eta 1, is the most informative.
So it trusts the paths that actually work.
Right. You want the model to be highly confident in the paths that actually teach it something useful about arriving at the correct final answer.
Think of it like navigating a massive dark maze. Standard entropy regularization is just you deciding to open random doors completely blind. You're technically exploring, but it's useless because you have no signal.
You're just walking in circles.
Exactly. But the IB score, specifically this covariance, is like having a finely tuned metal detector. You are still exploring the maze, but you are specifically choosing to open the doors where the signal on the detector gets stronger.
I like that.
You are aligning your confidence, your decision to move forward, with actual measurable information gain.
And the paper tracks this exact dynamic during training. In baseline GRPO, they show that this covariance rapidly drops to 0.
Wow, just flat lines.
The model quickly loses its intrinsic ability to align its confidence with high-value reasoning paths. The IB score, by being integrated directly into the optimization objective, mathematically forces the model to keep that metal detector turned on.
It forces it to care.
Right. It forces it to maintain that positive covariance throughout the entire training run.
Okay, so having a mathematically elegant score is great in a vacuum. But anyone who has actually tried to implement tree search on a large language model is probably screaming at their screen right now.
Oh, I'm sure they are.
Applying a complex metric at the step level across an LLM's entire reasoning process sounds like an absolute computational nightmare. I mean, hardware limits are very real. How is this actually implemented in a way that doesn't instantly cause an out-of-memory error?
Well, this is where we move from the theoretical math to the physical engine. They call it IB-Tree, or Information Bottleneck Guided Tree Search. To understand the efficiency, look at standard GRPO. You just run independent rollouts from the prompt. Say 8 separate API calls that share absolutely nothing but the initial prompt string.
Right.
In IB-Tree, you initialize a unified tree structure from the prompt.
And instead of just letting it run blindly to the end, it expands in iterations.
It does. In each iteration, it generates candidate steps. It then calculates the IB score for those specific nodes based on multiple rollouts, and here is the defining mechanic. It selectively branches only at the nodes, the top K nodes that have the highest IB scores.
So it's pruning as it goes.
Yes, it aggressively prunes the tree in real time, completely ignoring the low information branches.
But wait, how does it define a step in a continuous stream of text? Because if you have to evaluate this token by token, or if you have to run a separate process reward model to classify the steps, the compute cost would still be astronomical.
The engineering here is brilliantly simple. They just use the double new line character as the step delimiter.
Really? Just double enter.
Just to Nate. It's a natural training-free boundary that already exists in almost all chain-of-thought reasoning formats.
That's so simple.
And to prove its viability, they ran an ablation study where they added 10% random noise to these boundaries, basically forcing the system to under-segment or over-segment the reasoning steps.
And what happened?
The result. It barely affected the performance. The tree structure is incredibly robust to noisy step definitions.
Okay, my first thought is still about the GPU memory budget, though.
Yeah.
For those who haven't had to manage GPU memory lately, when a model generates text, he has to store the context of all previous tokens in the KV cache, so it doesn't have to recalculate them from scratch for every new word.
Right, which takes up a lot of VRAM.
Exactly.
Yeah.
If we are branching and creating all these different nodes, doesn't managing the KV cache for a tree completely destroy the token budget compared to just running 8 independent GRPO rollouts?
It's highly counterintuitive, but tree search here is actually significantly cheaper. Yeah. The Alibaba team specifically leveraged shared prefixes and technologies like VLLM's prefix caching to make IB-Tray remarkably efficient.
Break down the mechanics of that prefix caching for us. How does sharing a root node save memory in the GPU?
So if you are running 8 independent GRPO trajectories, and the first 500 tokens of the reasoning process are basically identical across all 8 runs, you are computing and storing those exact same 500 tokens 8 separate times in your KV cache.
Which is massive redundancy.
Massive. With IB-Tree, because it's a unified tree structure, those first 500 tokens are a shared root node. They are computed exactly once.
I see.
They are stored in the prefix cache exactly once, and all subsequent branches just read from that single memory block.
Wow. You're basically letting multiple different reasoning branches share the exact same memory footprint for their setup.
The paper proves this empirically. Under the exact same token budget as 8 independent GRPO trajectories, IB-Tree can generate 12 trajectories. 12. That is 50% more exploration, 50% more rollouts for the exact same compute cost.
That's incredible.
Furthermore, because IB-Tree expands iteratively, level by level, rather than all at once, the peak request width is only 4 compared to a peak width of 8 in standard GRPO.
So it literally halves the peak KV cache memory requirement during generation. That is a massive operational advantage for any ML engineer trying to scale this up on limited hardware.
It changed the entire economics of the training run, and once the tree is fully built, they calculate the final optimization by combining a standard global advantage with a local IB-based advantage.
Okay.
They found through their ablation studies that giving this local IB advantage a weight of lambda equals 0.1 proved optimal for updating the policy.
Okay, so we have a cheaper method that theoretically explores better. But, in AI paper slop, we need to see the receipts. Does this hardware-efficient theory actually translate to state-of-the-art performance on the leaderboards?
Oh, the empirical validation is incredibly strong. The team evaluated IB-TPO across the Qwen3 family, specifically the 1.7 billion, 8 billion, and 14 billion parameter models, as well as the Llama 3.1 8B instruct model.
Okay, good spread.
Yeah. They trained them using the DAPO Math 17K dataset. And across the board, regardless of model size, IB-TPO significantly outperforms vanilla GRPO.
What kind of numbers are we talking about on the heavy math benchmarks?
You see an average improvement of 2.9% to 3.6% across really rigorous benchmarks like Math 500, AIM 2024 and 2025, AMC 2324, GPQA, and IFEVL.
Those are tough benchmarks.
They are. To give you a specific standout metric, on the notoriously difficult AIM 25 benchmark using the Qwen3 14B model, IB-TPO hit an accuracy of 17.7%.
And what was standard GRPO?
Standard GRPO on that exact same model only hit 12.4%.
That is a massive jump on AIM. And looking at the charts, it's not just beating vanilla GRPO. The paper compares it to other advanced exploration methods as well, right?
Yeah, it clearly outperforms TreeRL, TreePO, and IBRO, which are all recent, highly sophisticated state-of-the-art reinforcement learning methods. But honestly, what's even more interesting than the final scores are the ablation studies they ran. They show exactly why the IB score is the critical component.
Let's hypothesize on those ablations for a second. If the shared prefix tree is so efficient, couldn't we just use the IB tree structure, throw away the complex IB score math, and just branch randomly?
You'd think so.
Right. Wouldn't we still get better results simply because we have 12 branches instead of 8?
You would think so, but the data says no. If you replace the IB score guidance with random branching or even a fixed width branching strategy, the F rate completely crashes back to 0.
Oh, wow. Why?
Because of those shared prefixes, the diversity of the final answers naturally decreases. If you branch randomly, you aren't finding the critical logical decision points. So all 12 of your branches end up collapsing into the exact same reasoning path anyway.
So you're basically just generating the identical wrong answer 12 times instead of 8.
Exactly that. Now, if you use entropy-guided branching, meaning you tell the tree to branch wherever the model is most statistically uncertain, the performance improves slightly.
Okay, so it helps a bit.
It's okay. But it's only when you use IB score branching, specifically with their optimal parameter of beta equals 5, that you yield the highest F rate and the highest overall accuracy.
Which proves the point.
It proves conclusively that the model needs to branch based on information gain, not just generalized uncertainty.
To really cement why this works for you listening at home, let's step away from the mathematical abstractions and look at the actual text generated by the model during these training rollouts. The paper provides some fantastic qualitative proof.
Oh, the case studies. Yes.
Yeah, case studies where you can literally see the semantic branches forming in the text.
These case studies are brilliant because they visualize what we call the synonym slop problem of standard GRPO.
Synonym slop.
Yeah. In one example, they show a model trained with GRPO and standard entropy regularization trying to solve a complex math problem. The model outputs multiple different trajectories, but when you actually read the text, the mathematical logic is completely identical across all of them.
It just looks different on the surface.
Exactly. The model is just swapping out synonyms to satisfy the entropy penalty. It says therefore in one run, thus in another, and hence in a third.
So it's technically fulfilling the mathematical requirement for entropy, but semantically, in terms of problem solving, it's identical, which means the reward verifier at the end is going to give them all the exact same score. 0 reward variance, completely wasted compute.
But when you look at the text generated by IB tree, because the IB score forces the model to branch where the information gain is highest, we see genuine semantic branching. The model actually explores fundamentally different ways to solve the problem.
The specific examples in the paper blew my mind. There is a coding problem they showcase about investor valuations. The prompt asks the model to evaluate 2 offers. One is a specific dollar amount for 10% equity, and the other is an amount for 20% equity.
And when you look at the visualization of the IB tree for this exact problem, the node with the highest IB score, the exact place where the tree decides to fork its exploration, happens right at the conditional logic.
Yeah, like one branch writes at first valuation, second valuation, while the other branch structures the Python code completely differently, calculating the base valuations first, before ever building the conditional statement.
It's actual logic branching.
It didn't branch at a random variable name or a comment. It branched at the core algorithmic decision point of the script.
There's another perfect example using a complex geometry problem about finding the area of a subtriangle. The tree evaluates the reasoning steps, and the highest IB score node occurs at the exact critical step where the model has to decide between two valid but completely different geometric strategies.
Which were what?
It had to decide whether to use the method of mass points or to calculate area ratios.
This is what makes this paper so powerful. The IB tree automatically identifies the critical crossroads of a problem. It finds the exact token or step where the path forks between fundamentally different reasoning strategies.
And it achieves this entirely unsupervised.
That's the crazy part.
It does not need a human-labeled process reward model to hold its hand and say, hey, this is an important step you should explore here. The internal mechanics of the IB score natively discover the pivot points of human reasoning based purely on the environment's final outcome reward.
It's an incredibly elegant bridge between outcome supervision and process discovery.
It really is.
So to wrap this all up, what we are looking at is a profound synergy. The IB score provides a mathematically grounded theoretical signal for where a model needs to explore. And the IB tree provides the memory-efficient physical infrastructure to actually execute that exploration without melting your hardware.
Well said.
Together, they effectively cure the sparse reward problem that plagues LLM post-training.
It really is a masterclass in taking a high-level information theory concept from representation learning and engineering it down into a highly optimized, production-ready training framework.
But before we go, here is a provocative thought for all the researchers and engineers tuning in. The paper proves that IB-TPO is incredibly effective for deterministic tasks, math, coding tasks, where the outcome-based verifier is an absolute true or false.
Right. You either passed the Python unit test or you didn't.
Exactly. The environment provides a stark, objective reward.
The signal is undeniable in those environments.
But what happens if you try to apply IB-TPO to subjective, open-ended alignment tasks?
Ooh, that's a great question.
Right. How would an IB score guide a tree search when the reward isn't a compiler, but subjective human preference? How do you even define information gain when there is no single ground truth correct answer for a creative writing prompt or a nuanced conversation?
That is exactly the next frontier. If someone can adapt the covariance of the IB score to handle the noise of a reward model trained on human feedback, you could potentially see these same 50% efficiency gains in general chat alignment.
It's definitely something to ponder while your next training run compiles. That's all for this breakdown on AI paper slop. Keep building, stay curious, and we'll catch you in the next video.